This is a lesson on reflection and flat mirrors in a unit on light and optics. In a prior lesson, I had talked about properties of light, and in the next series of lessons, I'm going to look at more applications of light. And to establish this, I need to talk about the ray aspect of light. The ray aspect of light is the model we use in sketches to be able to sketch and have a visualization of what light is doing. And we can see that light is modeled as traveling in a straight line, only in straight lines, and that's what we call rays. And this is a relic of mathematics. In mathematics, vectors and rays, they're all well defined there. And it's acceptable to visualize light rays as sort of laser rays through space. Okay, like light ray, and you can see this on the diagram here. A light ray will leave the sun and travel along a path, a straight path, to wherever it's going. Light may change direction when it encounters a reflective object, and we see that over here. The light hits from the sun, hits the car, and then passes through the glass and hits the person's eyes. All right, so there was a change in direction. Prior to hitting the car, there is a straight line, and after hitting the car, there is also a straight line. Rays are always completely straight, they never bend. So you can see that down here, always continues along a straight line. We do not draw curved lines when we think about the ray aspect of light. This is not an accurate model overall in science. We know that light curves along the surface of space-time, and so there is some curving of light. But in this model, as we draw rays, I will always draw them as straight lines through Euclidean space. So the first thing we're going to look at as we're applying light as a ray is the law of reflection. The law of reflection says when light encounters a smooth reflective surface, so this needs to be a smooth surface, it will reflect at the same angle at which it was incident, and we can see that over here. The incident angle we call theta I. We can see there's a little I down here, I for incident, and R is for reflected. Theta I equals theta R. This is one of the easiest equations you will see in physics. Because of this, I've made note down here, problem solving, when you encounter problems that apply this concept, often they are complex with strategies revolving around geometry and trigonometry. So you really need to know your properties of geometry and trigonometry in order to apply this in the most basic flat mirror situations. So I put a diagram down here. I like this one from OpenStax, and it kind of shows that even if you have a rough surface, light will reflect at an equal angle that it was incident, but we do not get a coherent light ray, a coherent bunch of light rays reflecting off this surface like we would on this flat surface, this flat mirror. So this is one of the studies, the most basic studies of the law of reflection is just a flat mirror. The law of reflection applies, and here's a diagram over here. You can look at it. And what I want to note is that we're looking at putting an image. Of course, if we have a mirror, we're putting an object in front of the mirror, and we'd like to view the object in the mirror. What happens is light rays leave the object, and I have a bottle here, it looks like. Light rays leave the object, and at each one of these points on the mirror, the light will follow the law of reflection. Because a bunch of light rays leave the cap here, we can trace two of them, and they meet up at the person's eye, and the person is able to see the light rays that left the cap on the bottle, hit the mirror, and then hit the eye again. What I'm going to note, as you see in this picture here, is that for each point on an object, let it be the cap or the bottom, etc., we need two rays. Notice how they've drawn two rays from each. And that's how you locate an image. And we can see the image here is behind the mirror. This is what we would call in front of the mirror, and this is what we call behind the mirror. And the image is behind the mirror, and this is what this equation says over here. Whatever the object distance is, DO, object distance, O is for object, D for distance. Whatever that object distance is, we will see that the image is behind the mirror the same amount. And if you use mirrors, many people do, that can be your experience, right? You are behind the mirror. The rays that actually get to the person's eyes were not directly from the object. They didn't go directly from the object. They went from the object, bounced off the mirror, and then got to the person's eye. The thing about eyes is that they're great biological instruments in order to perceive the world around us on some level. They could be better. But they're kind of dumb at the same time, because they don't know when eyes receive this light, the eye is not aware that it bounced off the mirror. It's not like a conscious thing the eye does. It's like this bounced. So the eye sees the image and thinks the image is behind the mirror. So when we focus our eyes, we're going to focus the distance from our eyes to where the image is behind the mirror. So you may see this in problem solving. You'll need to take that distance into account. And what we do is we call this a virtual image. Rays are traced from the object to the image. They leave the object, they bounce off the mirror with the law of reflection, and then we trace them to the eye, and the light actually goes along this path. And what happens is we trace the rays backwards, and that's how we can locate the image with ray tracing, is using two rays, allow them to bounce, and then let that ray that was received by the eye, not the incident ray but the reflected ray, extend that back behind the mirror, and then I can locate the image for ray tracing. The rays will reflect at the surface but may be extended behind the optical device to locate the image, and we need two rays to intersect in order to locate the image. So those are basics on mirrors in general and many optical devices, and we're looking at them specifically with flat mirrors to begin with. There's a lot of terminology to be aware of as we move into the optics unit. There's a ray, which I talked about. We're talking about incident and reflected rays. There's also refracted rays. Refracted rays go through materials, whereas reflected rays bounce off of materials. There's an object distance and an image distance. So we're talking about objects and images, and they each have distances. You might not be surprised that they have heights as well. We may look at magnification. That's another term in here that I did not magnification list in here. Did it get larger? Is it reduced? What's the effect of the mirror or the optical device on the size of that image? And that'll become more apparent as we get to maybe telescopes or microscopes, where we do care about what the relative size is. There's a radius or a center of curvature that we will get to. Focal length, focus, central axis. This is more in spherical mirrors. You won't see this with flat mirrors. But my warning here is be aware of terminology, and you may want to write a list for vocab words or look in the text for the list of vocab words so that you get used and become familiar, fluent, articulate with these vocab words. Again, down here, images, different types of images. A real image is an image created by the intersection of the original source rays. And a virtual image is the image located behind the optical device, formed by rays extended behind the optical device, so not real rays. So if I go back to this picture here, like I was saying, these are extensions behind the mirror, so this is a virtual image. When you look in a mirror, you look at a virtual image of yourself. It is not a real image. Your mind thinks it's real, like it perceives you there as real, but it's defined in physics as a virtual image. When we get to spherical mirrors, you will see how real images are formed, but with flat mirrors, it's always a virtual image. I picked a very simple example, a wardrobe mirror. You may have one of these in your house to be able to look at your whole body when you put on clothes and look at what your clothes look like on you. And so here's an image I borrowed from the OpenStax College physics textbook. And the woman is looking in a mirror. It says, suppose a woman stands in front of a mirror. Her eyes are 1.65 meters above the floor, and the top of her head is 0.13 meters higher. Okay, so when I look at this, they're giving me this distance from the floor to her eyes is 1.65 meters. So that's 1.65. And then it looks like an additional 13 centimeters from here to here, from her eyes to the top of her head. Okay, 13 centimeters. So that is the information we're given in the problem. What the question is, find the height above the floor of the top and bottom of the smallest mirror. Okay, so there's a lot of information. Find the height above the floor. So they want us to find the height at the top of the mirror, the height at the bottom of the mirror, and they want us to find this, I'll call this L, the smallest mirror, which she can see both the top of her head and the bottom and her feet in the mirror. And I like this picture. I could have done ray tracing. I will do some ray tracing with spherical mirrors. But the ray tracing is pretty much already done here. If the woman wants to look at her feet in the mirror, we can imagine a light ray leaving her feet, coming up and hitting the mirror. And then after it hits the mirror, theta I equals theta R, and then it hits the mirror and then goes up to her eye. And so these two angles are equal to one another. When her eye receives that information, it thinks that information came from down here, and it sees the bottom of the foot over here. What happens is the height above the floor that the bottom of this mirror needs to be then is just half the height between her eyes and her feet. That's all it needs to do, is just meet halfway in between. So this distance here, and I can put this in here, is going to be 1/2 of the 1.65. So that's 0.825 meters. Okay. So that's how far above the ground the bottom of that mirror needs to be. To locate the top of the mirror, it's pretty much the same sort of thing. We'll take light from the top of the head. It has to leave her head, hit the mirror, and then come back and hit her eyes. Her eyes sees that light originate from behind the mirror. And it'll be the same distance. Whatever distance she stands, that'll be the image distance behind. So what happens is that light only needs to hit halfway between the top of her head and her eyes. So that'll be 0.065 meters. So 6.5 centimeters from the top of her head, which is also 6.5 centimeters above her eyes. And we know the distance from the floor to her eyes is 1.65, and then we'll add an additional 6.5 centimeters to that. And so above the ground, the top of this mirror is going to be 1.715 meters. So that's how far above the ground that mirror, the top of the mirror, needs to be. And what we're going to note is that the height of this mirror, like how large it is, the length of it I put, is going to be, well, we know that this is 0.65, 6 centimeters here, 0.065 meters here. And then from here to here, well, that's half of the 0.65. So we're going to add on another, what is that? 0.825 again, right? Meters. So overall, this distance here is going to be half her total height. All right. It'll be the 13 centimeters plus the 1.65 meters, whatever that is. This is going to be half that. When you purchase a mirror to look at your body for your wardrobe, all you need is one that is half your height. So that answers this question over here. How is this distance related to the woman's height? The mirror, the length of this mirror from the bottom to the top is going to be half of the woman's height. So it turns out on this problem, if you do trigonometry and some geometry here, it doesn't matter how far away you stand from the mirror, as long as the mirror is half of your height and located right at that point where you can look down and see your feet. You will always be able to see all of you no matter how far you are from that mirror. I know it's an instinct to move closer and move farther apart in order to see more. And you may want to try this at home if you have your own mirror to see that you do not gain any more in sight if you move closer or farther away. What matters is how big that mirror and how it's located.